Thank you, Manu, for the introduction and invitation. I'm thrilled to be here with you. Today, I'll talk about compound and cascading hazards, their impacts, risk assessment. And before I start, I should acknowledge what I present is the work of my students, postdocs, and collaborators that I've had the honor to work with. Let me start with one example. What do I mean by compound and cascading hazards? Here are a series of events that happened in California. We had a 5-year drought that ended with a lot of rain. A lot of rain, obviously, is good news, but a lot of rain means vegetation growth, which is also good for the ecosystem, but vegetation is fuel for future fires. So in this specific set of events, after a lot of rain in winter, we had a very hot summer, dry and hot summer. So the vegetation dries out, and all you need is ignition. And that's exactly what happened. In December of 2017, outside the normal fire season, we had the largest fire at the time. We have broken that record 6 times now, but at the time. So you have a series of events, drought and heat waves, a lot of rain and local flooding, and then again, heat waves, Santa Ana winds, or sort of dry winds that set the stage for fires. And later, a month after that fire, we had an extreme rain event over burned areas that caused debris flow event. And unfortunately, 23 people died near Santa Barbara. So these are different events that happen over different scales. Some of them are long-term, like drought over a 5-year period. And some of them are very short-term. This whole debris flow event happened in about a couple of hours. So they have different scales. They happen over different times, but they are all connected. If you look at our current risk assessment models, we don't have methods that can capture all these different events that happen over different spatial scales, and more importantly, different temporal scales. In many of our risk assessment models, this time dimension is missing, this lag time between different events, especially events that are completely independent from each other. Now, in statistics, if you have independent events, what do? We multiply probabilities, look at joint probability. But it does not make sense in this case because, yes, the events are statistically independent, but they are dependent through impacts. And that makes it very difficult to build mathematical or statistical models that can capture risk over these different events over different scales. Another example is coastal flooding. Coastal areas, you can get flooded by the ocean. We call it ocean flooding. Also rivers, we call it fluvial flooding. And direct rainfall, we call it pluvial flooding. So these are different drivers. If you have a hurricane usually comes with surge, with extreme rain, and fluvial flooding. So you have all these events are kind of related, right? Hurricane dominates all of these drivers. But you don't necessarily need a hurricane. Even randomly, tide happens on a regular basis. So your extreme flood may happen just randomly at the time of high tide. So ocean water level above average. So even without a hurricane, you can have this kind of interaction between peak flows and ocean water level. So we call this compound flooding. If you look at USGS guidelines for flood risk assessment, it's primarily based on river discharge. So when it comes to coastal area, ocean water, there is no dynamics in terms of ocean water level, right? NOAA has a guideline for ocean water analysis. In that guideline, rivers don't exist. So we have numerical models, we have hydrodynamic models that we can use to simulate the physical processes, the interactions. But then when it comes to risk assessment models, the way we estimate like return periods of 100-year, 200-year flood for infrastructure design, we have a huge gap. Now, today, this area of compound and cascading hazards, many different dimensions. Today, I focus mainly on impacts and connection to the built environment. So, for example, we have different models, different tools to understand extremes, to simulate them. This is an example of high resolution satellite data, near real time that comes out of our center. But my question is, okay, I have this large scale data. How can I translate them into flooding or evaluate impacts on critical infrastructure systems? So this is going to be my focus. But let me start with coastal flooding, the example I started with. Again, we have multiple drivers, and we want to bring them all together for kind of comprehensive coastal flood risk assessment. How do we bring these drivers? Now, let's look at a kind of a cross section. I have ocean water level there, and this is a river that's draining to the ocean. This is just a one-dimensional view of this system. So this is my flood peak. So peak discharge is draining toward the ocean. If I have low tide situation and ocean water level is low, water can easily drain to the ocean. The amount of water that can drain into the ocean is a function of gradient, right? So if you have that gradient, the process happens easily. But what if you have high tide situation, like Hurricane Sandy? Hurricane Sandy in New York happened at the time of high tide, near high tide situation. That high tide made it a lot worse. So then the gradient is less water can drain into the ocean. Under extreme situations, in coastal areas, under extreme ocean water level, the river can even go backwards. We have a lot of examples of that already happen. So which makes flooding a lot worse. Now we want to bring these different drivers together. Where do we start? Again, we have numerical models that we can use to simulate individual cases. We're not interested in that. We have actually really good numerical models out there, 3D models, 2D models for this kind of problems. So we started with the basics. So this failure probability equation, it's widely used in different fields. It has different names in different fields. Some people call it the reliability equation, or we call it here failure probability, where P is exceedance probability of the event of interest, let's say 100-year flood. And T is design lifetime of what you're designing. This could be a seawall, could be a levee system, or some kind of infrastructure that you're designing for, say, 50 years or 100 years. In this case, and most traditional applications, we use, let's say, 100-year flood from USGS, basically, as input into something like that to get failure probability curve over time. So what we did, we extended this approach by using multivariate models. So instead of just P, single P, you have a multivariate model where you can have 2 drivers or even 3 drivers as input into that kind of risk model. So it's a multi-hazard concept. This requires, for example, using copulas, but also it requires hazard scenarios. I'll talk about hazard scenarios in a moment. So the details, I've included the references, and you're welcome to get a copy of the slides. So let's look at this notion of multivariate failure probability. So failure probability, you can draw its y-axis failure probability, x-axis is design lifetime or time, T, design lifetime. So if you have a univariate case, USGS flood frequency in New York City, you get the black line. So this is what you typically get from USGS for flood risk assessment. And obviously, failure probability increases over time. But then if we extend this to multi-hazard case, we get the red line here. So you can see that for any given time, there is like 10%, 20% underestimation. So if you ignore the compounding effect of these drivers, you underestimate flood risk. Again, Hurricane Sandy is a classical case. You can look at Hurricane Sandy at high tide and average ocean water level condition. The difference is huge. And that is what is missing in our current risk assessment guidelines. FEMA has a guideline that supposedly accounts for both drivers, but always assumes that one driver is average, like historical average. Even that underestimates flood risk, and we have another paper specifically on FEMA's method. The good thing about this approach is that you can replace historical ocean water levels with future sea level rise. Then you get the purple line. You can have multiple models and get upper bound and lower bound. By the way, failure probability here is not physical failure probability. It's kind of hydrologic failure probability. If you design something for a 50-year flood, let's say a seawall, if 50-year flood happens, it's hydrologic kind of failure, but the wall may not physically fail. For physical failure, you need another type of model, and I'll talk about it very briefly in a moment. So this method was published in 2017, and then ASC adopted it in the manual of practice. Now it's the only kind of manual of practice method out there. ASC is going to turn it into a code, but it will take a long time. There is a committee now that's working on this kind of transition from manual of practice is one level before like a code. So we are moving toward this direction. And I think it's really important because it has significant impacts. We have done this over different places. The general pattern is the same. Everywhere you underestimate coastal flood risk if you ignore the compounding effect of different drivers. And the underestimation, overestimation is different, depends on the strength of the relationship between drivers, but the general pattern is the same. But there is another important component that we have systematically ignored, and that's land subsidence in coastal flooding. So if you look at existing methods for coastal flood risk assessment, methods that we use in most of these methods were started from hydrology frequency analysis and then evolved into guidelines. We ignore land subsidence, but in many places, in New Orleans, for example, land is going down relatively fast. In some parts of California, many other parts of the world, Indonesia, many places, there's significant land subsidence. So in that case, the relative difference between land and sea level is changing. So even if nothing else changes from climate perspective, your flood risk continuously increase. How do we capture that? Some of our tidal gauges have GPS sensors, and when you get ocean water level, some of the land subsidence is captured there already. But in most places, that's not included. Even those that capture land subsidence, they only capture the long-term signal, not the seasonal part. Here's an example. This is Houston, Texas. And you're looking at land subsidence, vertical land motion in this area. As you can see, there is significant spatial variability. This is based on radar-based satellite data, so kind of SAR-based information. So even within this relatively small area, there is significant difference in terms of land subsidence. How do we bring that into our coastal flood risk assessment? So this is, let's say, you have sea level rise information. How do we correct this for seasonal land subsidence? Because in many places, you have ups and downs in your vertical land motion because of groundwater seasonality and so forth. And that can make a huge difference in your flood risk. So here is an example application. We've developed a kind of framework that brings that into account. So first, let's say you're looking at a 20-year flood based on USGS, so univariate traditional method. If you do compound flood risk assessment, that 20-year flood turns into something like an 11-year flood. If you add land subsidence, it changes to about a 6-year flood. How did we come into this area, to this field? So I've had funding through DOD, and once they invited us to go to Galveston area, basically there is a Coast Guard base and an Army Corps base next to each other here in Galveston area. And they observed that frequency of floods are way more than basically all these guidelines give you. Like they get flooded way more often than what theoretical guidelines show. So we started looking in this problem, see why it's happening. So one element is the compound flooding, but even that doesn't explain everything. That was when we realized, oh, it's land subsidence. When you add all of them together, then everything makes sense. Why that area gets flooded so many times. And all of these components are missing from our formal guidelines for risk assessment guidelines. Okay, now this method is statistical, right? Remember, we use river flow data, ocean water level, right? But we don't distinguish between different systems. Here is a coastal area in Alaska. There's a lot of open space. And let's say if because of sea level rise, this estuary disappears, another one will evolve further upstream. There's a lot of space, maybe a different environment, but there is room for evolution, basically. Here, this is a coastal environment near where I live, with significant urbanization on both sides. This is a very small and limited estuary. Estuary is like our flood coping capacity. Like it's your area that allows you to manage flood water, distribute it. If we lose this to sea level rise, it's gone forever. So how do we bring this physical element? So to do that, you have to build a different type of model. So this is important as driver, but then you need a physics-based model. And with collaborators, we have developed this kind of connection between hydrologic failure and physical failures. So this is used as input into a finite element model of a levee system. This is an example from Levee in California, where you have this model that physically describes the levee system, and we force it with different scenarios of compound coastal flooding, and we get physical failure probability. So that one is statistical failure probability. This is physical failure. And we can look at, let's say, 50-year physical failure probability. And you can look at it under historical climate and future climate. This is the example in this case, but you can run different kind of scenarios. Could be different historical scenarios. Now, this example was coastal flooding, but I want to take a step back and talk about different types of compound and cascading events. A few years ago, we formed an informal committee and worked on different ideas in this space of compound and cascading hazards, and we broadly put them in these 4 categories. We have multivariate compound events. Those are events that have some kind of relationship in terms of drivers. You can describe the relationships. For example, coastal flooding is an example of multivariate compound events because we have tools, models that we can use to describe the relationship between drivers. In this category, events typically happen at the same time or very close to each other in most cases. Then we have spatially compound events. For example, floods that happen in different areas, but they all drain into one location. For example, 2016 Baton Rouge, there was a 1,000-year flood. But if you look at rainfall, it was not that extreme, but there were many extreme rainfall events in different tributaries of the Mississippi River, and they all drained into one location. That's an example of a spatially compounding event. Then precondition means, for example, rain over snow. Rain, especially warm rain over snow, can cause flooding. It's very common in Europe, in snow-dominated regions. The snow is the condition, and rain is the trigger. So in this case, sometimes the drivers are not related. Sometimes they are not. But the condition is really important for this form of compound event to happen. The last category is temporally compounding, or a better term, I think, is cascading hazards. in case of cascading hazards, sometimes the drivers are related. Sometimes they're completely independent from each other. They have even different physical drivers. So I'll talk about these events, but let me talk about these three. Cascading is a little bit more complex, and I'll get to it toward the end. But for these three categories, over the years, we have tried to develop tools that can be used for different types of events of this type. For example, multivariate copula analysis toolbox is a package designed broadly to capture different types of extremes, including their relationships. And the second one, multi-hazard scenario analysis toolbox, is designed to develop hazard scenarios. And hazard scenario is really important for planning purposes, and I'll talk about this in a moment. The source codes are available, and we have also a version that includes a graphical user interface where you can load your data and just run the model without having to deal with the code. But everything is available. There are many built-in models, and you can ask basically this package to find the right model for your own application. So let me go a little bit deeper into hazard scenarios. So what do I mean by that? So when we talk about, let's say, 100-year flood, and we are dealing with only river flow, it's a straightforward concept. But what if you have multiple drivers? Let's say ocean water level and river flow on the x-axis. So this 100-year flood or 50-year flood can be defined differently. Here are two different hazard scenarios. One is called and hazard scenario, the other called is or hazard scenario. Or hazard scenario means you're looking at flooding by either or both drivers, right? So the other one, and hazard scenario, specifically look at two extremes kind of happening at the same time. And as you can see, in this case, 50, these are 50-year joint return periods. They are very different. They're different curves. They are very different, fundamentally different. For different types of applications, we need to choose the right one, and that requires a lot of work. And in this package, not only we have these two popular ones, but there are some other ones like Kendall and so forth that we have included there. And in addition, we have a method that looks into likelihood of these joint events to happen. For example, within this joint, let's say 50-year return period, the likelihood of there are infinite combinations of ocean water level and river flow that will give you this 50-year flood. But the likelihoods are not the same. So we have a framework in GRL, the source code is also available, that basically, based on historical data, will tell you what are the likelihood of these points. And when it comes to risk assessment, remember in this example, I mentioned that you need to have a physics-based model. You need to tell this model what is 50-year flood. And in this case, you have many, many different combinations. So the hazard scenario gives you different types of forcings. In this case, we used 6,000, but different types of forcings as input so you can get a realistic view of physical failure probability. Again, the hazard scenario part is, I think, something important that's missing in our literature. By the way, the term return period, again, is designed based on univariate values. When it comes to multiple dimensions, it loses its original meaning, and the community hasn't come into consensus on how to define it. That's a whole different story, active area of research. But now let me show you some other examples. Here, we are looking at drought and heat waves. Again, a different type of compound events. So I'm showing an example application of this method. We are looking at CDFs, cumulative distribution functions of drought and heat waves for two different periods. The latter period is the red line, and this shift to the right means more drought and heat waves are happening together. And if you look at temperature and drought data, we see that, in the southwestern US, where we are, overall, in the past 50 years, we have seen about 0.6 Celsius of warming. But if you look at droughts alone, the rate of warming is about twice higher. There's this kind of amplification of warming. There are many papers out there on physical reasons. There are established relationships with soil moisture depletion, impacts on sensible heat, and so forth. I don't want to get into that part. The question is, how do we need to look into risk of drought when you have patterns like this? We see that you have this amplification of warming. How do we need to update our drought risk models to account for this amplification of warming, or this kind of change in co-occurrences of drought and heat wave patterns? So as an example, let's look at any given year. For example, 2014 year, drought, it was a drought year in California. It was a very impactful year in terms of impact on the agricultural sector. It was one of the worst. We had water supply problems, and at that time, there was even some kind of rationing on water distribution. There was a mandatory 25% water use reduction from the state. So it was a really, really extreme year. And if you look at rainfall data, that's what we often use to describe drought. It was fifth on record, that specific year. We have about 120 years of data. So empirically, it's like a 25-year event, 24, 25-year event. So still an extreme year. It was not the worst, but in terms of impact, it was. So if you look at temperature and precipitation using the same method I mentioned earlier, this is temperature anomaly, this is precipitation. It's just inverted. So warm and dry is on top right, and this is the opposite, cold and wet. So with the same approach, this turns out to be a 200-year event, which is more consistent and the worst on record, which is more consistent with the impact data. In terms of impact, it was the worst in terms of drought impacts. Now, let me switch to a more complex case, since we are in College of Complex Systems. So this is a case of snow temperature fire dynamics. These are different events that often happen in different scales. So the story is we've always been interested in snow and snow dynamics, and we studied how snow amount in terms of depth, snow water equivalent, SUI, this is snow water equivalent, and also center of gravity changes from year to year. So these are PDFs of snow water equivalent for different levels of warming. So these PDFs refer to historical data about 1 degree below average, blue, 1 degree above average, red. So small differences in terms of mean temperature, but you see the PDFs change significantly. These are all for one specific time of the year, April 1st. That's the kind of end of the snow season and reference for snow evaluation in California. So this means that even 1 degree change has a significant impact. You can connect the dots here and see 1 degree warming is equivalent to 20% change in snow water equivalent. And we rely on snow. 20% is huge. So this is, by the way, why we were interested in this kind of putting everything in perspective of temperature change. After Paris Agreement, there was this debate between whether we should try to limit warming by 1.5 degree or 2 degree. And this discussion emerged in media. What difference does it make? 1.5 versus 2? What is the significance of 1 degree? So we tried to put that 1 degree in perspective at least here with respect to snow water equivalent. So that was the motivation why we focused on this 1 degree warming. And we did the same thing for center of gravity of snow. And of course, this later evolved into this snow drought model. That is, I believe, is still the only global snow drought data set available. So the idea is that if you're evaluating drought, you have to look at snow separately, because we had years in California where we had above average rain, but very severe low flow conditions in summer. So drought condition in summer, but above average rain. And we noticed snow is the one that explains everything. So if you look at snow, those years you have snow drought. So snow drought is basically below average snow for the time of the year. So at the same time, when we were working on this topic, of course, we have group meetings and we present these ideas, right? Another student was working on fires. And we noticed that fires are happening at higher and higher elevations. These are fires in California. And this is elevation in thousands of meters. So these are fires happening at 9,000, 10,000 feet above sea level. Areas that used to be too cold or too wet to burn, but now they are burning. So not only burned area is increasing, but fires are happening at higher and higher elevation. By the way, this was 2018. We just updated. I have to use the updated version. So this is still going up. So this trend is continuing kind of upward. So this is really concerning. Now, these fires are happening at high elevations above snow line. In some places, snow line in California is around 2,000. In some other places, it's even lower. So some of these burned areas will later receive snow. And our question was that, okay, so snow, so let's say fire happens in summer and snow that happens maybe 6 months later. These are independent from each other, but they're definitely related through other processes. Imagine you have this burned area. Now it has very little canopy. Very little canopy, so snow is more exposed to solar radiation. So we expect rapid snow melt. Rapid snow melt means higher chance of flooding, right? And also it means higher chance of drought. So we started looking at this issue first using satellite data. So the strategy is finding burned areas and identifying nearby unburned, so we can relatively compare changes. So let's say we identify burned areas, red, and we find equal number of pixels in unburned areas because we want to isolate the effect of climate variability. It's hard to do, but that's the only thing you can do, like comparing burned and unburned. So you assume that kind of climate is more or less the same. So the difference you see is kind of because of fire. And we look at residency time of snow on the ground, radiative forcings, and this is still under review, but what we see is that we see warmer summers, but colder winters. So colder winter is detectable from space. And I think it's because with little canopy, snow accumulates faster on the ground, and you have little interception. So the skin temperature goes down, and you can detect it, but it melts faster. And because of that, we believe that both flood risk and drought risk change at the same time. And the coupling between like transition, rapid transition from flood to drought is probably intensifying, especially in snow-dominated regions. And that's a work in progress, but we are also doing field work for the same idea. So we go to burned areas, we find the boundary of the fire, we take samples from burned and unburned, and we compare. These are very close by samples. So you can argue that rainfall is the same. So these samples are maybe just 200, 300 feet apart from each other, but on burned and unburned side. For example, this is soil moisture in burned versus unburned, surface temperature burned versus unburned. And you see there's like 10-degree difference. And that one is subsurface. Subsurface, that's surface temperature. So 10 degrees temperature difference is a huge impact on snow melt and soil moisture and lots of other. So that's the part that requires a lot of work to understand these processes. The challenge is that, again, fire happens usually in fire season, in summer and fall, and snow is completely independent in how to bring them together. One part is understanding that has its own complexities, but then how to quantify change in, let's say, flood risk and drought risk, or joint flood and drought, or coupling of these two. That's the hard part that needs a lot of work. I'm looking forward to brainstorm with you, Manu, on some of those aspects later tonight. So there's an assignment. So there are lots of opportunities. Again, this is very complex system, but lots of interesting opportunities. Now, another dimension I want to add to the same complex thing, this issue of non-stationarity in data. If you look at rainfall extremes in many places, you have this significant trend. This is the N-year concept over the whole world, North America, Northern Hemisphere. If you look at just extremes, in some places, overall rain has not changed, but extremes show some kind of an upward trend. So there are methods to account for non-stationarity, and those methods, some of them are standard. We have our own approach. We call it process-informed non-stationary extreme value analysis that not only does the traditional way of non-stationary analysis, but it allows you to bring in potential physical drivers. I know Manu has worked in this space. For example, bringing in land use, land cover change to look at change in runoff. Or this could be some kind of circulation pattern, like CO2 emissions for temperature, that's another example. So if you look at, use this method, this is an example of building IDF curves, in rainfall intensity, duration, frequency curves. Again, we use IDF curves for design purposes, but the current methods, the existing one is stationary. It ignores trends and patterns. So the blue line is what you get from NOAA. So the x-axis is days, is duration, y-axis is intensity, and this is 50-year IDF curve. And if you use a non-stationary model, our version, you see that the red line, and the method allows also bringing in future simulations, of course, with bias correction. So this trend in extreme precipitation will interact with the significant increase in fire trends. And in this specific case, what we consider as 50-year event will turn into a 29-year event, means it will happen more frequently. Now, remember, I mentioned that these burned areas are increasing. This is burned areas in California that has a significant upward trend. We have our own fire model that kind of simulates burned areas with different climate drivers. The details are in this paper, but now this rain over burned area is a good issue to talk about cascading hazards. So we talked about these 4 areas. The last part, this temporally compounding or cascading hazards, very complex. So burned areas are increasing, and at the same time, extreme precipitation is increasing. So just by chance, rain over burned area can also increase. But these events are independent from each other. Yes, rainfall that happens shortly after fire, usually there is a relationship through aerosols, but in most cases, these are completely independent. So back to this example, how to bring this rain over burned areas into risk assessment models. This is a very difficult, it seems simple, but it is not. So we have looked at it empirically. Empirically, it's very simple. You look at everything that happened in the past. We have historical records from fire, historical data from rain, and we can generate our PDF of rain over burned area. So this is the blue line, and we have done it with future model simulations. And for any given threshold, you can look at area under the curve and see how your risk is expected to change. So by just simply looking at area under the curve. But how do we translate this into a formal risk assessment model? So we don't have a solution for this yet, but the two methods we are exploring. One, we're doing backward analysis, starting with event, and then using learning algorithms to find the drivers. And the idea is that if you can basically build a backward model, then once you have confidence in it, then you can run it forward. Most risk assessment models are top-down. You start with the driver, then you go to impacts. But here we want to try to do this backwards, impacts and non-impacts, see if we can differentiate between them. And the other approach that we are exploring for this is basically going away from the concept of events. And again, another topic that I want to discuss with Manu, of if there is a certain event, let's say fire, the events that follow, we don't look at them as individual events, but as a kind of aggregation of extreme and non-extreme events. We don't have a solution yet, but hopefully down the road, but this is one of the areas we are very excited about. Now, there are some interesting cascading hazard cases that require our attention. When we look at droughts, mostly we look at geographical location of drought. So this is what we usually produce. But we know impacts propagate across space through trade networks. Food goes from one country to another. There are seven or eight major food producing countries that kind of dominate the food network. And again, since we are in the School of Complex Systems, how this complex network works, how impacts of drought, let's say in the US, can propagate in other countries. We have evidence of this in the past. Like in 2011, drought in the US caused increase in food prices in Kenya. We know that Russians banned export after the major drought and heat wave event in 2010. Food prices went up crazy in Syria, probably contributed to protests and civil war. So these events have happened. So we try to take our drought model to the next level by building a trade model into it and look at the cascading impacts throughout the world. So this is a model that converts drought, geographical location of drought, to change in calorie supplies. So instead of looking at individual crops, we combine everything, rice, wheat, canola, and all major food products, we convert to equivalent calorie. This is an example of change in calorie supplies in response to 2002 drought in Canada and part of the US. So there was no impact, obviously, in the US and Canada, but these are places where you see significant change in calories. Some of the countries like Saudi Arabia are rich. They import way more than what they need. So again, no real impacts, but there are some other countries that don't have much of a cushion, and any change in calorie will translate into significant health impacts. That's another direction we are exploring. And more recently, I'm interested in compound climatic and non-climatic events. For example, what's the impact of a major drought in the US and Australia and war in Ukraine? War is completely independent, non-climatic. But we know that, for example, this is data from Egypt. Yellow is the amount of wheat they are importing from Ukraine. So here is one country that imports from different places, including Ukraine, the US, and some other places. What if you have this drought that happens every once in a while, and we can quantify the risk, and let's say it's happening now, and put a current war or a potential war, the impacts on the food network, who will be impacted and how? And this is still not published yet, but we're translating this into an online tool where not only you can look at historical events, but you can run hypothetical scenarios of climate extremes and non-climatic events like riots, wars, disruptions, and so forth. This is another case of complex cascading hazards where you have very different drivers, completely independent from each other, and often from very different natures, like climate and non-climate. So I think we need to push toward this notion of impact-based monitoring of these events, these extremes, whether we are looking at individual events, droughts, or compound cascading hazards. Most of our current modeling systems, again, let's say drought monitoring, they just show where the drought is happening, and that's it. That's where we stop. I think that's where we need to start. So in the next few years, I want to focus on linking existing modeling systems or monitoring systems to actual impacts, physical impacts, impact on infrastructure, impact on food, people. Here is an example, again, where I can quickly, how much time I have. So I try to very briefly show you one example where we translated snow drought into impacts in the agriculture sector. So we have this global snow drought model. So we know where we have deficits, and a model that, and a kind of global model that translates snow to runoff, and we have global irrigation data. So with that, we can, and we have global data from US Foreign Services, USDA Foreign Services on irrigation from around the world, and also World Bank and FAO. They have this data. We have combined everything available from these three sources. So this is share of snow in irrigation water for different crops globally, including time of the year where irrigation water is needed. So this allows us to look at deficit at that time of the year and translate it to change in irrigation water and impact on maybe crop yield. So we've generated this kind of snow hazard index. Again, this is based on snow drought. So these are hotspots, places where basically if you have below average snow melt, it will translate into below average irrigation water. So we have generated this global maps of impacts on different crops. So wheat, rice, maize. So basically, if you see a global, if you have a global map of snow drought, through this modeling framework, you can translate it into potential change in these crops. So basically translating snow drought to impact on agriculture sector. Usually there is a lag. When you see drought, it takes a while before you can see the impacts. And that lag, if we build these models properly, then we have usually between 3 to 6 months to plan or look for alternative sources. That's an example, but this is not, this has to be developed for each type of hazard separately. And finally, I'd like to highlight one project that I'm very excited about on global transboundary waters managed by the national academies. It involves many different partners from around the world, mainly focuses on Central Asia, North Africa, and the Middle East. And we are developing this kind of vulnerability assessment framework that involves not only traditional terms like drought, water availability, water stress, but also water demand and some other human-related terms like government effectiveness, human development index, GDP, indicators that we sometimes ignore, but they are very, very important, that they basically focus on coping capacity. So there is an early version of this model that will be released this summer. As an example, this allows us to compare countries for based on different metrics. For example, this is energy per unit agriculture production per, for example, kilogram of food. And this is water consumption, again, normalized per kilogram of food. The dotted lines are global average, and the color bar is production per capita. So you can evaluate countries or even individual basins in a relative sense. There are places where they produce a lot of food, but using below average, global average waters, but there are countries that produce very little food, but use a lot of water and energy. And hopefully with that process, you can identify places where you can potentially improve efficiency. So this is, again, another area that I'd like to focus on, and not only for drought, but bringing drought, floods, heat waves, and fires all together, hopefully down the road. With that, I hope I've convinced you that compound and cascading events are important and exciting to work on. And these are my students and postdocs who do all the hard work. Be happy to take any questions you may have. Thank you.